Okay, so today we'll continue with our discussion of intrinsic and extrinsic semiconductors. I believe we stopped right here. Right. So as a brief recap, we're talking about silicon, intrinsic silicon. If we start at absolute zero, meaning 0 Kelvin, there are no free carriers, there are no broken bonds. Each silicon atom is bonded with its 4 neighboring atoms. Each one of them shares 1 electron with 4 neighboring atoms. And so you have 4 plus 4, 8 atoms create a stable bond. As the temperature rises from absolute zero, going all the way or coming all the way up to room temperature, which is 300 Kelvin, that is approximately 27 degrees C, around 80, 85 Fahrenheit. Some of the electrons acquire enough energy to break free of their bonds, and they move around. And they now move around into the lattice structure. Okay, so they break their bonds and they're moving around in the lattice structure. Okay, and these free electrons, when I say free, meaning they're free to move around. So if they move in response to an external applied electric field, they are moving charges. When charge flows in a circuit, energy is transferred. That is defined as current. Right? Rate of flow of charge is current I, dq over dt. And so this is known as an intrinsic semiconductor because it is intrinsic to the material. However, the number of these electrons is not sufficient. Okay, compared to a metal, or compared to an insulator, it's large, but compared to a metal, it's not sufficient to actually conduct electricity. Okay, so if an electron moves out, what happens? When an electron moves out, it leaves behind an empty spot. Right? You have an electron, it breaks a bond because of acquired thermal energy, and it breaks, once it moves out, it breaks that bond, leaves behind an empty spot. That empty spot is a hole. They couldn't come up with a better word, so they used a hole. And because it has moved out of a spot, the atom has lost an electron, but that electron originally also had a corresponding proton in the nucleus that is not free to move around. Okay, so it helps to treat that hole as a particle in its own right, and we assign a positive charge to that particle. So we get what is known as a hole, and a hole is said to have a positive charge. So if you lose an electron, the answer is yes, you are positive. And again, I give credit for this meme to Professor Chuck Bland. So here is one example. Electron jumps to fill the hole, and thus a hole is free to move around also. Remember, we are still talking about intrinsic semiconductors. Temperature rises at room temperature, which is basically this environment right now. The electrons have acquired enough thermal energy to break free of their bonds. Once they break free of their bonds, they move out of their spot, leaves behind an empty spot. These electrons are free to move around. The number of electrons that are free to move around is much larger than are present in an insulator, but are far less than what is present in a conductor. Right? So hence a semiconductor, it's somewhere in the middle. Yes. Okay, so this actually should be an electron that is moving. And because an electron moves here, the hole is moving to the right. So so the question being asked is, how is the hole moving? So let's do a small illustration. So if I have, no, so these are not holes, these are simply points in a lattice structure. Okay, you don't have to draw this. All right, so let's say all of these were occupied by electrons, all of them. Okay, and then let's say an electron breaks free. Electron breaks free, goes here. Okay. Actually, you know what? Let's start, instead of here, let me start the other side. Let's say I have an electron here. It breaks free of its bond. It's moving around the lattice structure. It finds another empty spot somewhere where another electron has left. So this electron jumps here. Okay. So that means this spot right here is empty. Yes. Right. Now that's an empty spot where another electron can move into. You all with me so far? So now you had a opening or a hole here. That hole moved here because the electron moved to the left. The hole moved to the right, right and up. And then another electron jumped into that spot. Thus, that hole is now here. So the electron is moving in one direction. And because that hole is here, another electron can move into that spot, which creating a hole here, which means the hole has now shifted towards the right. The hole is at this point right here. Right here. Does everybody see that? It might be a little bit blurry or faint. Another electron can jump into that spot. That means it created a hole here. So now a hole has moved there. So every time an electron moves, the corresponding empty spot is moving in the opposite direction. Does that make sense to everyone? Right? And so early on, when they were doing research in this device physics, they decided that if electrons are treated as negatively charged particles, sorry, not treated, but electrons are negatively charged particles, then we can treat the absence of an electron, we call it a hole because it's an empty spot, and it helps tremendously in terms of calculations and understanding to treat the hole as a particle in its own right. And that particle has positive charge. Okay, so when we talk about semiconductor physics, we talk about electrons, we talk about holes as particles in their own right. Electrons have negative charge and holes have positive charge. And so again, holes, electrons move one way, holes move in response to the exact opposite way. Does that make sense? Let's take a pause. Let me know if you have any questions. Any questions from anyone? Okay. All right. So intrinsic semiconductors. Talked about how without any external interference, if you have a piece of semiconductor material, if it's sitting at room temperature, comparing that room temperature energy to the energy it had at absolute zero, you have a large number of electrons that are free and available. And so those number of electrons is referred to as N. N for number of electrons. And the subscript I means it is inherent or intrinsic to the material. There is no other energy that is supplied to that material other than the intrinsic thermal energy that is present in the surrounding environment. So it is known as an intrinsic semiconductor, and the number of electrons that are available are designated as Ni. Okay, intrinsic background concentration of electrons present in the atomic structure. So silicon and germanium are intrinsic semiconductors. They have, at room temperature, they have some free electrons available. And the number is 1.5 into 10 raised to 18 atoms. And each atom would have a free number of electrons. So 1.5 into 10 raised to 18 times electrons that are freely available. It seems like a huge number, but actually it's not. Okay, compared to an insulator, it is a large number, but compared to a conductor, any metal, for instance, that's a small number. Okay, so what can we do? Well, what we like to do is we like to create or increase the number of electrons that are available, right? In a conductor, such a large number of electrons are available that there is no energy band gap, right? The energy levels overlap. In a semiconductor, there is a band gap. So we impart enough energy, or we increase the number of electrons, and also we impart energy to those electrons. So what we do is we take some external material and we introduce it into our intrinsic semiconductor material. And because it does not originally belong in that material, it is referred to as an impurity. Impurity is something that doesn't belong in there. Okay. And so adding impurities, meaning you simply add some external material into your sample. Adding or introducing external material. Okay, external material. So you have intrinsic semiconductors that have some intrinsic concentration, and we introduce external impurities into that material. And the word that we use for this material, as well as for the process, is doping. And I heard it for the first time, I couldn't believe it. So you take the external impurity and we call it as we dope the intrinsic material. So we create a doped semiconductor. Doped semiconductor, and the impurity is known as a dopant. So it's called either a dopant or an impurity, or it's also referred to as a dopant impurity. Okay, dopant impurity. In a conductor, there's so many free electrons present that if you add or introduce some impurity in there, it actually creates more problems, because the free electrons are now colliding with the electrons in the atoms that are introduced in there. So it actually restricts the movements of the electrons that are already present. That makes sense? You already have a large number of free electrons present in a conductor. You introduce more in there, but now the electrons that are free to move around are now colliding with the external impurity dopants. And because of that collision, current flow is not as efficient. Okay, and because it's not as efficient, the net effect is that the resistance of that material has now increased. And hence, if you introduce some impurity in a conductor, it increases the resistance of that material. Whereas for a semiconductor, if you add an impurity, you're now introducing more free electrons in there than were available previously, which means now it can behave like a conductor. And so the net effect is that it decreases the resistance. And because it decreases the resistance, we can manipulate the resistance, the resulting resistance, by controlling the dosage of that dopant impurity. And the dose is typically 10 raised to 19 to 10 raised to 22 atoms per centimeter cube. Background concentration was 10 raised to 18. Intrinsic concentration is 10 raised to 18. External impurity is 10 raised to 19, 10 raised to 20, 21, 22 atoms per centimeter cube. It's a huge amount. Okay. Tens of thousands of orders magnitude large. Yes. Is it? Oh, yeah. That should be centimeters. Thank you for pointing that out. Yeah, good catch. It should be centimeter cube. Okay, let's take a pause. Let me know if you have any questions. Does it make sense so far? Okay. Okay, so we are introducing external impurity dopants, right? Silicon has 4 atoms in its outermost shell. If you pick an element from column 5, it has 5 electrons in its outermost shell. If you pick an element from column 5, then 4 of those 5 electrons will bond with 4 silicon atoms. It will displace a silicon from its lattice, from the lattice structure, and occupy that spot. And once it occupies that spot, let's say if it's arsenic or phosphorus, it's going to form a bond with 4 neighboring atoms. 4 plus 4 leaves behind 1 extra electron. So if you're flooding a tiny spot in your semiconductor material with 10 raised to 20 atoms, you now have 10 raised to 20 free electrons, which is a far larger number than 10 raised to 18. Make sense? So you now have that many free electrons. So this is a free electron. It is free to move around anywhere in the material. And this one here is also a free electron. Okay. So you have now a plethora of electrons available to freely move. And because this has negative charge, we call this as N-type semiconductor. Okay, so we created a N-type material from our intrinsic semiconductor. 。 . 。  . 。 . 。 . . . . . . . 。 . 。 . . . . 。 . . . . . . . 。 . . . 。 。 。 。 . . . 。 。 。 . . . 。 . . 。 . . . 。 . Make sense? Each extra electron is an extra negative charge. However, the overall charge in that material is still neutral. Because the arsenic or the phosphorus atom came in, right? It brought along 5 protons and 5 electrons. So even if that electron is now free to move around, it is still balanced. Overall, it is still balanced by the positive charge that is bound to that atom inside the nucleus. So electron is free to move around, but the positive charge is not. So you have negative charges moving in there, but overall, the charge is still neutral. Okay? It has now become an ionized atom. If the electron leaves and moves, it becomes an ionized atom, but overall charge is still neutral. Does that make sense to everyone? Right? So the overall charge is still balanced. Okay. On the other hand, if we take column 3 elements like boron, this shouldn't be arsenic. This should be boron. And this should be plus. It's a lack of electrons. So actually, let's just cancel it out. Okay. Boron or gallium from column 3. So if you take a column 3 element and you introduce it into our intrinsic semiconductor, what do we get? We have 3 electrons. It forms bonds with 3 of the silicon atoms. And there's one empty spot, meaning there's a hole that is present because of only 3 electrons, the impurity. And because of that, we now have an extra positive charge. Hence, we obtain what is known as a p-type material. So column 3 dopants create a p-type material. Overall charge is still neutral. Okay, overall charge is still neutral. So now you have p-type material, you have an n-type material. What can we do with those? Right, by itself, not much. It's just sitting there. If you hold it in your hand, it's just sitting there, not doing anything. But if you bring it in close proximity, if you combine a p-type material with an n-type material, that's where the magic happens. Okay, this is a 2-dimensional illustration of a p-n junction. Okay, p-n junction. This is not how it's actually fabricated or actually manufactured. Okay, we don't create p separately and n separately and bring it into close contact. Okay, we have a p-type material and we simply insert an n-type inside it. But let's say you have a p-type material, you have an n-type material, you bring it in close contact. What happens? You have excess of holes on the left and excess of electrons on the right. Right? Holes and electrons. When you bring it in close contact, there is a charge imbalance. And because there's a charge imbalance, the holes cross over the junction and electrons also cross over the junction in a bid to neutralize that imbalance. Okay. Again, holes we are talking about as particles, but they are empty spots. So if you have electrons, if you have an electron here, which sees an empty spot, it is going to jump into that empty spot. Not all of them, but some of them. And when that happens, we call the process as recombination. So electrons combining with holes simply means an electron is moving into an empty spot. And that process is known as recombination. And when recombination occurs, it takes out the negative charge, it takes out the positive charge. So one negative charge disappears, one positive charge disappears. Overall charge is still balanced and neutral. Okay, so holes and electrons recombine and the charges disappear. And that happens right at the junction. Okay, and it keeps happening. And so this junction grows. Now, conventional wisdom would dictate that if you bring it in close contact, P and N, holes and electrons crossing over, they're recombining until, and then it'll keep continuing until all of the charges are crossed out and rebalanced, right? But that's not what happens. And that's how we are able to actually create devices. What happens is, because the holes and electrons combined to take out the charges, there is a region that is created right at the junction, and that region is devoid of all charges. It is depleted of all charges. Hence, that region is known as the depletion regions. Depleted of all charges. Okay, it's completely depleted. The only thing left over in the depletion region is holes on the N side and electrons on the P side. Okay, because they are now the minority carriers that are left over. Okay, now this is a non-E major class. So this is as far in depth as we will go. I'll just talk about it a little bit more, but we won't go into the equations. We won't go into anything else. I am teaching EE306, which is basically the semiconductor class for EE majors, which is right at 11 o'clock. So if you are interested, if any one of you is interested, I would welcome you to come and learn more in depth if you want in that class. Okay. But I'll go over the basics of what happens here. You all with me so far, right? You got holes and electrons that cross over, recombination takes place, it takes out the positive and negative charges. So that region is completely devoid or depleted of all charges. Hence, it is known as the depletion region. You would expect that the depletion region would keep expanding until everything is neutralized, all the charges disappear. But that's not what happens. What happens is, because of the movement of the majority carriers, meaning the electrons on the N side, electrons on the N side and holes on the P side, when electrons move out, what is left behind are empty spots. And so you have these holes on the N side and these electrons on the P side. Okay, and this movement gives rise to an internal electric field. Okay, there are holes and electrons present as minority carriers in the P and N side. So it gives rise to an internal electric field. That internal electric field opposes any further movement of the electrons and the holes from the N and the P side. And so this barrier is established, that region is established, that start expanding until that electric field reaches a level that opposes any further movement of the holes and electrons. And so it expands and it settles at a particular spot. And it creates a physical barrier between the P and N type. And this barrier requires external voltage or external electric field to overcome. That gap that is established depends on the material property. If you create your P and N type material from silicon, the external voltage that is required to overcome is around 0.6 volts. It's typically around 0.6 to 0.7 volts. Depending on the author, depending on the textbook, you might come across 0.6 or you might come across 0.7. But that is an inherent material property. Okay, depending on the number of electrons and the holes, doesn't matter what the doping is. It doesn't depend on the number of electrons or the holes. Okay, if you create it out of silicon, it's about 0.6 to 0.7 volts. If you create it from germanium, it's around 0.2, 0.3 volts. And this is known as the built-in junction potential. The movement of the holes and electrons creates a barrier. That barrier needs a certain voltage to overcome. Remember at the beginning of the chapter, I said we will study these are non-linear devices. We'd apply a voltage, but the current is not going to increase proportionally. So if you apply 0.2 or 0.3 volts to a silicon diode or silicon junction, then current will still be zero because it has not yet overcome, hence nonlinear. Okay, let's take a pause, think over all of that, and let me know if you have any questions. Any questions? Okay. So we brought it together, called it a PN junction. And because the behavior is exactly or highly similar to the vacuum tube diode, they carried the nomenclature over and they call this the solid state PN junction diode. Two electrodes, the P-type silicon and the N-type silicon still carry the same labels, anode and cathode. The symbol is a triangle or an arrowhead with a vertical line. The line indicates it's the cathode, and the tail end of the arrow is the anode. Anode is treated as positive, cathode is treated as negative. They are noted by the letters A and K. A and K. In real life, you have these diodes, and they are noted by a colored band running around the cylindrical structure. Okay. In your lab kits, you'll have these diodes that are about this size, very, very small. This is actually a very good image of the actual diode. Okay, there will be about black epoxy material and a silver gray band running around on one end. And the terminal it's closest to is the cathode. You also have Zener diodes in the lab kit. They're plastic transparent packaging, and I believe orange or red, maybe black bands running around one end and wrapping around at one end, and that black band indicates that's the cathode. So always have a band closer to one terminal, and that terminal is the cathode. That's how you would identify it. So PN junction diode. Okay. So if you create this diode out of silicon, requires 0.6 or 0.7 volts to turn on. If you create a germanium diode, it's 0.2 to 0.3 volts to turn on, meaning before you apply 6 volts, before 0.6 volts, there's no current flow. So we say it's on or off. And we'll talk about that in just the next few slides. Every time electrons flow, I mean, current flows through, electrical energy is being transferred. A lot of that energy is dissipated and lost as heat. Okay, so these devices, these semiconductor devices, get hot depending on, the size, the power, the energy that is being applied. Okay, so every time current flows to these devices, they get hot because the energy is dissipated as thermal energy. There are special types of semiconductor devices that are made from multiple elements. So those are not intrinsic. Those are known as compound semiconductors. And some of the most common ones are made using column 3 and column 5 elements. So the most common ones are gallium arsenide, gallium phosphide, and gallium nitride, which nowadays in many of the consumer chargers, you may have heard about it. Gallium nitride fast chargers, right? Also, gallium arsenide is basically a compound semiconductor that dissipates energy in the form of heat and in the form of light, from which you get light emitting diodes or LEDs. And depending on the dopant impurity that you introduce into the gallium arsenide material, the wavelength of the emission is different, and hence you get different colored LED lights. Okay, so compound semiconductors. So again, semiconductor devices dissipate energy in the form of heat. They do get hot, and many of the compounds dissipate the energy in the form of light. There is a little bit of energy dissipated as heat. So you'd have, but the light energy dissipation is a whole lot more higher than the ones dissipated as heat. So LEDs, they are bright, but they don't get as hot as filament light bulbs. Okay, talk about forward bias and reverse bias. Okay, we have plenty of time. If you take the anode and cathode of a PN junction diode and you if you connect the anode to positive and cathode to negative, we say that the diode is forward bias. What happens is P-type material has excess of holes, N-type material has excess of electrons. You connect it to positive, the holes are repelled, the electrons are repelled. And if they're repelled, they are pushed in this direction. All right. If you impart sufficient energy, that barrier is now overcome, and the holes and electrons will cross over. Electrons start flowing through the circuit. Electrons are moving up. Which direction is the current flowing? In the opposite direction. Current is flowing down, I. If you think back to circuit analysis, it all adds up. For a supply, current always goes from minus to plus. Right? So you get lots of current flowing through the circuit. Now, when it says or shows here, you're connecting a positive voltage to the anode and negative to the cathode, doesn't always mean has to be positive with reference to 0. It just means that the anode is held at a higher potential than the cathode. Okay. if the anode is held at a higher potential than the cathode, the diode is forward bias. Does not necessarily have to be 0 volts at the cathode. Okay, it could be 3 and 2 volts, 3 at the anode and 2 at the cathode, and the diode is still said to be forward bias, because the net effect of those voltages would mean that the diode is and anode is held at a higher potential. So in circuits, this is of course just a single diode connected to a single battery, a single voltage source. But in circuits, diodes are part of much larger circuits with lots of components. So as long as the anode is higher than the cathode, diode is forward bias. So anode is greater than cathode, it's forward bias. On the other hand, if we flip the polarity, now the cathode is higher than the anode. What happens? Electrons that are there in the n-type material are now attracted. See the electrons here, they are attracted by the positive terminal of the battery. Same thing happens at the other end. The holes are attracted by the negative end. And so the barrier, junction barrier, keeps on increasing because the holes and the electrons are now pulled away from the junction. And because they're pulled away from the junction, the depletion region increases in width. So the barrier increases. So there is very little current flow through the junction. Okay, almost zero. It's so small that we cannot measure it with just regular instruments. Okay, it's like 10 raised to minus 12, 10 raised to minus 15, like picoamps and femtoamps. Even when we perform experiments in the lab, it's very, very difficult to measure those small, tiny amounts of current. Okay, because the only current flow that is taking place is due to the minority carriers. So in reverse bias, we say that in forward bias, there is current flow. Reverse bias, there is no current flow. If there is current flow, we say in forward bias, the diode is on. In reverse bias, diode is off. But again, that's 2 slides later. So here I would say, if the cathode is greater than the anode, then we say that it is reverse bias. Okay, it's reverse bias. All right, let's take a pause. Let me know if you have any questions. Anyone? Yes. It is, and yeah, and it's not dumb. I mean, it's a very valid question. To be honest, I don't know the answer. My best guess is C is reserved for capacitor, C is used for Coulomb. C is also, let's see, there's also 1 other 2 cases where we use C, but capacitor and Coulombs come to mind. There's also the reason current is, is noted by I. Rate of flow of charge. There's only so many alphabets, right? So. I guess it's the C, the alphabet C can be pronounced with an S, or a K. And so my best guess is because they didn't want to cause confusion, they just chose K. Cathode. Okay, an analogy can be made with a mechanical valve. So diode is a one-way device. If you have a mechanical flap valve like this, if fluid flows from left to right, is going to force this valve to open, right? Goes up there, which is right here, which allows the fluid to flow through. So the fluid flows through, it's one-way direction. However, if the fluid flows in the opposite direction, it's going to force the valve to close. And if flow is coming in the opposite direction, it's going to force it to close. So no fluid flow or no current flow. So you can make an analogy of a diode with a mechanical flap valve. Make sense? Right. So it's a one-way device, and we can hold off that discussion for next class. So one-way device, if it's forward bias, we tend to say it's on. If it's reverse bias, there's no current flow, we tend to say it's off. So we'll end class here today, and I will see you all on Monday. First thing on Monday will be the quiz. Topic will be kind of similar or the same. Simply ask you to do something about Thevenin and Norton. For the offline quiz for Friday, you have the entire weekend to get that done whenever you want. I will be in my office later on this afternoon, actually right after my class today. And I'll be there till at least 4. So if you have any questions, feel free to stop by, send me an email. And I'm still available for a few more minutes until the next class here. All right.